Now that we have studied basic requirements, let's focus on the core functions of the cluster power manager. As initially claimed, two basic variables can be used to manage power in a multiprocessor cluster. First, available execution parallelism. This reflects directly in powering down unused CPUs. Alternatively, unused CPU's clock can be turned off. Second, performance demands fluctuate temporarily. Given the communication requirements between CPUs operating in the common coherent address space, these CPUs should run at the same frequency and voltage level to ensure low snoop latencies. CPUs in non-L1 coherent operation, however, can assume independent performance levels through individual frequency and voltage change. Both variables, together with CPU communication requirements, give rise to four individual processor states which each CPU can assume. These processor states are coherent mode, non-coherent mode, clock off mode, power down mode. The state diagram shows possible transitions between those processor states and their effects on power, frequency, and voltage. Within coherent mode, frequency and voltage follows the peak performance demand of the parallel coherent application. However, individual CPUs can leave or join the processing of coherent data and assume the non-coherent mode. Now, frequency and voltage can be adjusted individually according to each CPU's performance requirements. Non-coherent CPUs are also permitted to migrate into clock-off mode, which eliminates power consumption caused by dynamic recharging of circuit capacitances. In this mode, only leakage currents remain. Optionally, voltage can be reduced to a low level to maintain processor state. Such an ultra-low leakage state is called state retention. A fourth processor state is power down of a CPU. Power gating implementation employs switching transistors to gate off CPU supply rails towards the primary supply network. Within power down mode, special implementations of CPU registers and SRAMs allow state retention. Migration between those four processor states is managed through the cluster power controller. Critical observer might have noticed that clock off as well as power down mode provide independent means of CPU state retention and will ask why there should be an individual clock off mode rather than simple power down with retention. The answer lies within the configurable nature of the cluster CPUs. Implementers might not choose the silicon area overhead associated with state retention solutions, or don't want to expand silicon area in power intent verification effort to implement power gating. In such case, clock off mode and voltage reduction for this CPU can provide viable alternatives. However, the implementation choice comes with an increase of wake-up latency since external voltage regulator programming times and slew rates must be awaited before clock can be reapplied. Let's step now to an example of cluster and CPU power modes. The leftmost picture shows all CPUs in coherent operation. Coherent snoop traffic is routed through the central coherence manager and forwarded to all CPU peers. All CPUs operate at the same frequency and voltage level to minimize snoop latencies. The picture below shows CPU 2 has left the coherent address space and operates in non-coherent mode. Bus access for this CPU is supported by the central coherence manager and is routed directly towards higher memory hierarchies, such as the L2 cache. CPU 2 will not receive and emit snoop messages and is allowed to operate at any requested frequency. Voltage for this CPU can be adjusted according to frequency requirements. All other CPUs can remain in coherent operation. The top rightmost picture shows CPU 2 in clock-off mode. No CPU internal operation or bus traffic towards the central coherence manager is performed. The voltage for this CPU can be lowered to a state retention level. However, a trade-off between wake-up latency versus leakage power reduction will ultimately dictate the amount of voltage reduction. The right bottom picture finally shows CPU 2 in power-off mode. Local supply rails for this CPU are gated off, and special isolation values are driven towards surrounding logic. This is a requirement since CMOS logic inputs cannot be left undriven. Specialized standard cells provide a switchable isolation behavior. After we have now outlined the basic modes of operation for cluster power management, let's look closer at the central power controller. The controller provides cluster-wide power gating as well as clock and reset control. It is a programmable platform peripheral and is accessible through cluster CPUs. Wake-up of power domains is initiated through external events or CPU peer access to the controller. As a platform peripheral of the 1004K cluster, the controller connects directly to the Coherence Manager fabric and provides access management for a cluster-wide global address space, as well as per CPU localized address ranges. In order for a CPU to access the local address space of a CPU peers, special access privileges must be present. As depicted, each power domain consists of a set of programming and setup registers and a dedicated command sequencer. Besides setup and status inquiries, 4 basic commands are executed: clock off, power down, power up, reset for the CPU. The power sequence generated depends on the given commands and the previous domain state. As an example of a typical power sequence generated from a domain, let's send a power down command for a CPU in non-coherent operation. The clear bus signal is raised to request the conclusion of existing bus traffic. After bus traffic has finished, clock control is disabled to freeze the processor state. Now isolation cells are enabled to disconnect the CPU. A retention save pulse is created to write back flop contents for retention flops. Real enable is deasserted, which causes the power gating. Let's now focus on software control aspects of a power-managed processor cluster. At its core is a power-aware operating system which responds to immediate performance demands of running applications, collect temporal performance statistics, and, based on those statistics, might predict future performance requirements. Performance data for all current hardware threads are translated for each CPU. The resulting performance level is also used to calculate an appropriate target processor state for each CPU. Thereafter, a device driver will communicate both processor state and performance level to an SoC frequency voltage controller and a cluster power controller. Within the operating system, performance levels are the primary control variable from which processor states are derived. Since each CPU provides 2 hardware threads, optimization of overall processor states might cause the migration of hardware threads into different CPUs to free up the CPU for power down. The power-aware operating system will exert 2 basic control functions. First, unused CPUs will be powered down. Second, the OS modulates cluster frequency and voltage according to current and future demand. As an example for the use of performance level and processor state, let's have a look at the ACPI, the Advanced Configuration and Power Interface specification, which provides a standardized way for the operating system to communicate with hardware power management functions. The overall system state is reflected in 4 states G0 to G3. This state space is a reflection of all devices and processors within the system. Each element is assigned a discrete performance level and processor state. ACPI implementations can be found, for example, in Linux distributions. However, other operating systems, such as Windows CE, as relevant for the embedded space, provide similar definitions of power management functions. Let's now bring all components together and look at an example of a power-managed 1004K processor cluster within a system on chip. The operating system inquires current processor states for all CPUs through the cluster power controller and the frequency voltage controller. Current and predicted future performance demands determine the new processor states and frequency settings. The cluster power controller will execute processor state targets for all processing cluster components, whereas a frequency voltage controller communicates with programmable voltage regulators, frequency synthesis, and clock preparation components. These in turn will change CPU frequencies and determine up and downstream frequencies between the processing cluster and SoC-specific functions.